तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
All right. We will begin today with the problem of a charged particle in an electromagnetic field, but before I do that I would like to make sure that we have clear our ideas about basic electricity and magnetism. So I am going to start with a bit of a lengthy digression, 15 minutes to start with, on basic electricity and magnetism. It might grow into 50 minutes, but it depends on what you already know and what you do not. So let us start with the basic equations of electromagnetism, and here is E and M in a nutshell. So let us do that first. E and M in a nutshell. After a lot of experimentation, it turns out that all of electricity and magnetism at the classical level can actually be compressed into 4 equations, the 4 Maxwell equations. So let us write them down and then let us see what we can do from them, with them. So I start off by saying the first equation is the divergence of the electric field. This is the charge density, and I will use standard international units, so it is rho over epsilon naught. The second equation is the divergence of B, that is equal to 0, the curl of E, this is equal to minus delta B over delta T, and the curl of B, which is mu naught J plus mu naught epsilon naught delta E over delta T. These are the 4 Maxwell equations in free space, and I am going to only deal with the free space case. And as you can see, there are 2 equations for the divergence of the electric and magnetic fields and 2 equations for the curl of these 2 electric fields. Now the first question, I am going to do this in a Socratic method, so speak up loudly, give your answers loud and clear. Is this equation valid even if this field is time dependent? Yes, indeed it is. So these are actually fields in space and time, so this equation is valid for arbitrary electric fields, and similarly this too. How about this equation? Is it true only for steady currents, or is it true only for steady magnetic fields, or is it true for, it's clear from the right hand side that it should be time dependent. Can the field change from point to point? Is this true in general? Yes, indeed it is. So these are field equations, and therefore this is a function of r and t, and this is a function of r and t as well, and similarly here too. Completely arbitrary space time dependent quantities here, and these are the 4 Maxwell equations. I am going to ask a series of questions about these equations. The first of them is, how many unknowns are there? What are the knowns and what are the unknowns? Rho and J are the sources of the electromagnetic fields. They are supposed to be specified, and you are supposed to calculate E and B. How many unknowns are there in E and B? 6 unknowns. And how many equations are there? Well, if you have 6 equations and 4 unknowns, you are in deep trouble.
But E can be derived from a potential.
We do not know anything yet. This is all we know. These are the equations, and this is crystallized wisdom starting from Coulomb's law in a generalized form leads to this equation. The fact that there are no magnetic monopoles leads to this equation. This is Faraday's law of electromagnetic induction, and this is the Ampere-Maxwell theorem. In the absence of electric fields which change with time, and for steady currents this was the original Ampere theorem, and now it is the Ampere-Maxwell theorem with its displacement current put in. That is it. These are the equations that are given to you. And how many of them are there? How many equations are there? There are 8 equations, because these two are vector equations and these are scalar equations. So if you go by components, there are 8 equations, but then that is an embarrassment of riches. You have 8 equations and only 6 unknowns. In general you do not have a solution then. Too many equations, too few unknowns, no reason why there should be any solution at all. And yet we know there are electric and magnetic fields all around us and these equations work, they are right. So what would you say is happening?
Something is redundant.
There are some redundant equations, or at least there are connections between these equations which are not apparent here. So there really are 6 pieces of information for 6 unknowns, but they are jumbled up and they are mixed up in a crazy fashion, and we are going to unravel that. We are going to see in what fashion they are really mixed up. So there are really only 6 independent equations, and the reason is there is a connection between the J and the rho, the source terms here. They are not independent of each other, because as soon as you say charges cannot be created or destroyed, there is a connection between J and rho. You do not specify them independently. What is the connection between them? The equation of continuity, and this is certainly true in the absence of sources and sinks. Del dot J equal to 0. So there is such a connection. There is a similar connection between the magnetic charge density, which happens to be 0, and the magnetic current density, which should be sitting here and is 0. So you really have another constraint equation which is equivalent to saying 0 plus 0 is equal to 0. Now that is a constraint too, it is just that it is not apparent here. So you really have only 6 pieces of information, and we will see this in another way very shortly. What is the difference that you can see immediately between these 2 equations on the one hand and these 2 on the other? Pardon me? Well, given these equations, there is no magnetic charge and so on, given these equations, there is a basic intrinsic difference between the first and the fourth equations on the one hand and the second and third on the other. There are no sources. These 2 equations involve the sources and these equations do not involve the sources at all. Therefore these equations are valid independent of the sources. All electric and magnetic fields must satisfy these equations. So let us make that clear by writing this, bringing this to the left hand side and writing this as plus delta B over delta T equal to 0, and this of course continues to be equal to 0. So these 2 equations on a slightly different footing from the other 2 equations, and let us bring the E to this side and let me write this as curl E, forget the R and T for a moment, minus mu naught epsilon naught delta E over delta T equal to mu naught J. Oh, this is not good. Now there are no sources in these 2 equations, so there is another way of saying that these equations are different from these 2 equations, and what is that? Well, the right hand sides of these equations are 0 and not so for the other 2 equations. So what do you call these equations? In which? Homogeneous equations. These are homogeneous and these are inhomogeneous. Now that we have the homogeneous equations, let us exhaust the contents of these equations first. Put in all the information that you can get from it and then substitute it in the first and fourth equations. Now what is the first conclusion you can draw when you hear that a vector field B is identically divergenceless? What conclusion do you draw from it? We know that the divergence of a curl must be 0 identically. So you have this vector identity which says the divergence of the curl of any vector field, let me call it V, is equal to 0, is identically 0 always. And therefore this equation implies immediately that B can always be expressed as the curl of another vector field A. You have exchanged your ignorance of B for your ignorance of A, but at least you have exhausted the contents of this equation.
How does that imply
because you know that the divergence of a curl is identically 0, and since the divergence of B is identically 0 for all magnetic fields, B must be the curl of some other vector field always, with no exception. We do not know the other vector field, but it is always so, and you will see the advantage of introducing this A. A has a name, it is called the vector potential. Let me not call it the magnetic vector potential, because you will see that A is going to play a role in E as well. It is just the vector potential. Why do I call it a potential? It is not potential energy, it is a historical hang up. The fact is that you know that in the old days, if you had a scalar potential V as a function of position and you took its gradient, you got the force, and this very often in mechanical instances had the implication of being the potential energy, and you differentiated it in order to find the force, the vector field. So that name got carried over, and since you take this vector field A and you differentiate it, after all the curl operation is some kind of derivative, and you produce another vector field B, you call it the vector potential. Vector because A is a vector, that is the only reason for it. So anything you differentiate to produce another field, you call it a potential. It does not have a connotation of physical potential or anything like that, it is not a potential energy anything, but it is just an auxiliary field which you introduce whose curl is going to give you B. Okay. Now I put it to you that once you have written B in that form, A of course is also R and T dependent, you have exhausted the contents of this equation, that is it, there is no more information that this equation affords. But you put that in here and you promptly discover that this implies that the curl of E plus delta A over delta T is identically 0 once again. Now notice that I have taken the curl operation del cross and delta over delta T and I have commuted the two, and the reason is these are partial derivatives and therefore you can differentiate in either order, it does not matter. So curl of delta B over delta A over delta T is the same as delta over delta T of curl A. So I mix the two up and then I get this, I interchange and I get this, but this again affords us some simplification. It says this vector field E plus delta A over delta T has no curl, it is identically curl free or irrotational, and what quantity has the gradient of a scalar field is identically, has 0 curl identically. So of the gradient of any scalar quantity is identically 0, and therefore the contents of this equation are completely taken care of, because once you write E plus delta A over delta T as the gradient of some scalar field, that is it, this equation is taken care of completely. So this would imply that E plus delta A over delta T equal to the gradient of a scalar field, but let me put a minus sign here purely as a matter of convention, and the reason is in electrostatics you know that E can be written as minus the gradient of a field phi, a scalar field, and this phi has the connotation of being the potential energy of a set of charges. So we keep that minus sign for that reason, no other reason, and write E plus delta A over delta T in this form. Okay. What would I call phi? I call it the scalar potential, not the electrostatic potential. This has nothing to do with electrostatics, it is always true. So this becomes, therefore let us write our two basic equations. One of them is B equal to the curl of A and E is equal to minus delta A over delta T minus the gradient of phi, that is it. The fact that I can write these two equations, these two fields in this form, derives directly from the two homogeneous Maxwell equations, and that is it, their contents are completely taken care of. So I erase these two equations and I am left with those two. What have I done so far? Well, I got rid of B and E in terms of auxiliary quantities A and phi, and the idea is if you solve for A and phi you can solve for E and B by differentiation. by these rules, but I have gained an advantage. The fact is these are 2 vectors, so there are really 6 numbers sitting here, but a and phi between them account for only 4 of them. So it means that these homogeneous Maxwell equations have ensured that all E and all B can be found from 4 quantities, not 6. That is enough to find all of E and B. Incidentally, these identities are completely trivial to prove either component wise or in index notation, because in index notation the divergence of the curl of V, the curl of a vector field, its ith component would be epsilon I j k del j v k, where this is delta over delta x comma x sub j, the x component, and then the divergence of that would be epsilon I j k del I del j v k with a contraction over I and j, because the ith component is like del dot this guys, and that is del I and then the ith component of this curl. This is it, but this is a symmetric tensor in I and j, this is antisymmetric in I and j, and you have to sum over all possible I j k, and the contraction of a symmetric tensor with an antisymmetric tensor is identically 0. So it is a trivial statement that the divergence of the curl of a vector field is 0. Likewise, the curl of the gradient of u stands for the ith component of this curl, for instance, would be epsilon I j k del j, that takes care of this, and then del k on u, that is the kth component of the gradient of u. Once again this is antisymmetric in I j in j and k, and you got this which is symmetric in j and k, and therefore it is 0 by contraction. This also tells you that there is no other possible vector identity in 3 dimensions. This is it. These are the only 2 identities that you have to really remember, and we have put that in, and this is what we get. And now let us go back a little bit and ask, these 4 Maxwell equations, they are first order partial differential equations. They are first order for a very deep reason, which we will try to get back to a little later, but they involve the divergence and the curl, and I want to explain to you why they involve only the divergence and the curl. So please remember that we also had this equation divergence B equal to 0 and curl E plus delta B over delta T equal to 0. Okay. My question is, why do we specify, what is so special about specifying the divergence and the curl of a vector field? Why not anything else? Because after all, if I have a vector field V which has got components v1, v2, v3, then you can differentiate each component with respect to each of the coordinates, and really you have 9 derivatives possible. So you have del I vj, or if I write this out, you have delta v1 over delta x1, delta v1 over x2, x3, x1, x2, x3 stand for x, y, z, and v1, v2, v3 stand for the x, y, z components. Then you have delta v2 over delta x2, x1, v2, delta x2, delta v3, 2, x2. So you have these 9 components. You could actually put it in a little matrix of this kind. You have 9 possible partial derivatives, and what does the divergence correspond to? The sum of these diagonal elements. What does the curl correspond to? It is a vector, well no, it is a vector, it is this minus that, and that gives you the 3 component of the curl. This minus that gives you the minus 2 component of the curl, and this minus that gives you the 1 component of the curl. Now why is it that out of the set of 9 quantities you choose the diagonal 3, you call it something, call it the divergence, and it is a scalar, and why do you choose the antisymmetric differences of the off diagonal elements and you call that a curl, another vector field? And the answer is that it turns out that when you take a tensor of rank 2 of this kind, the sum of the diagonal elements, as you can see, is going to be invariant under similarity transformations. It is not going to change, we know that the trace does not change, and this means under rotations this quantity will not change. That is the reason the divergence is a scalar. And it turns out that the differences between the off diagonal elements is a vector, transforms like a vector. So very specific transformation quantity law is implied, and we would like to have all physical quantities expressed in terms of objects whose transformation properties are known to you. That is why objects can become, physical laws can become form invariant, the same for all observers if you like, and this is the reason why you choose these two particular combinations. But a deeper question still occurs, and that is, how do we know we do not need any other combinations, any other derivatives? Why are these alone enough? And the answer is buried in a theorem due to Helmholtz, which says that if you give me, in rough form it says, in a region of space, if you give me the divergence and the curl of a vector field and you specify the normal component of the curl on the surface of this volume element, of this volume, then the field is uniquely determined. So we take recourse to this theorem in vector analysis, which says essentially that specifying the divergence and curl is in a sense enough. It is sufficient to determine the vector field completely. But having said that, you would still like to understand physically what does it mean to specify the divergence and curl, and here let me go back a little bit and give you an example where this comes from and what the reason for it is, and that is important to understand, because every equation in mathematical physics that you see would always involve vector fields with divergence and curl, and the reason is buried in this theorem, and you would also like to understand why this is sufficient. So let us heuristically understand why it is sufficient to specify the divergence and curl. Let us go back and ask, what is the solution to an equation of the form d over dx f of x equal to lambda f of x. This is an eigenvalue equation in which d over dx is the operator, differential operator, f of x is the eigenfunction, lambda is the eigenvalue, and f of x is again the eigenfunction. What is the solution to this equation? The solution is f of x is, apart from a constant, it is e to the lambda x. So you agree that e to the power lambda x is an eigenstate or eigenfunction of the derivative operator. Now let us generalize this to 3 dimensions, and instead of lambda I would like to take something like ik. So I ask, if I took e to the power I k dot r, where k is an arbitrary constant vector and r stands for the 3 position components x, y, z, this is a scalar function. I put an I because I am thinking in terms of waves, I am thinking in terms of oscillatory functions, cos and sine functions and so on, which I can combine into e to the I k dot r. This stands for e to the I k1 x plus k2 y plus k3 z, and I ask, what happens if we took the gradient of this? That is a scalar function, and I am asking what happens if we took the gradient of the scalar function. So what is the answer? Yeah, it is ik times e to the I k dot r. So you could now say that e to the power I k dot r is an eigenfunction of the del operator with eigenvalue I k. Now that is a vector operator, so its eigenvalue is also a vector, and it is I k. That is a very simple result, as you can see. What is the physical meaning of this result? Well, if you put e to the I k dot r equal to constant, the surfaces you get correspond to k dot r equal to constant. That says k1x plus k2y plus k3z equal to constant. What sort of surface is that? It is a plane in space, and the gradient is normal to this plane, because the gradient of a scalar field is always normal to its level surfaces. So it gives you the direction normal to this plane, that is what this is telling you. But what is this? Del dot some constant vector, let me call it a, e to the I k dot r. What is this equal to? A is a constant vector, k is another constant vector, the r dependence, the coordinate dependence is sitting in e to the I k dot r, and I do del dot this, what happens? So you must take the x component of this guy, which is a1 e to the I k1x plus k2y etc., differentiate it with respect to x, and similarly for the y and z, and add up these three. It's a simple matter to verify, it is a 2-line thing to verify that you are going to get ik dot a e to the I k dot r. K is a vector and a is a vector, so you find the dot product of k dot a, and it is multiplied by the scalar function e to the I k dot r. So in a sense it is turning out that the eigenfunction of del dot is a e to the I k dot r for arbitrary a and arbitrary k, and likewise it is not hard to see that del cross a e to the I k dot r will turn out to be I k cross a e to the I k dot r. So even del cross has exactly the same kind of eigenfunction. Now that is marvelous, because it is really telling you that if you give me a vector a e to the I k dot r, that is a vector field where a is any constant vector, then this vector field is acting as an eigenfunction for del dot and del cross, the divergence and the curl. So what it is doing is to take the divergence and curl operators and converting them to numbers, it is converting it to algebraic quantities. So differential equations are getting converted to algebraic equations, and what is that trick called when you convert a differential equation to an algebraic equation? It is called Fourier analysis. This is exactly what you do, you convert the derivative operator to multiplication by k, by the Fourier variable, and this is what has happened. So now we know that if you give me an arbitrary function of r, I can expand it in a Fourier basis if it is a respectable function, and since these are linear equations, I can superpose the equations for each component and reconstruct the field, and for each component those things are valid here. So what is this telling you? It says that the divergence of this vector field is I k dot this guy. So it says the divergence tells you the component of this vector field along the direction of k, and this says the curl of this vector field is I k cross, and therefore this curl operator, this guy here, is telling you this is normal to the direction of a. So it says in sum that the divergence equation is going to give you, along any arbitrary direction you choose, the divergence equation is going to tell you how much of that vector field points along this arbitrary direction, and the curl equation is going to tell you how much is in the normal direction, in the transverse direction, and together they determine the entire field. So this is the reason why all these equations involve divergences and curls, independent of coordinates, independent of observers, independent of what your coordinate system is. So it is carrying a dictionary which is independent of the observer. No matter what k direction you choose, the divergence will give you the longitudinal component and the curl will give you the transverse component, and that is true for every k, and you superpose all possible k's, you get your field. So this is the reason why the Maxwell equations specify, this is the reason for the theorem, the Helmholtz theorem, which says if you tell me the divergence and the curl of a vector field, I tell you, and plus some suitable boundary conditions, I tell you the field uniquely. And the reason is the divergence equations give you the longitudinal components and the curl equations give you the transverse components, independent of the direction of the field for every k. So is this clear? That is the real reason why you have divergences and curls appearing everywhere in physics. Okay, now that we know that, let us put these things back and ask, what do these equations tell us? I am going to plug this equation back in here, and what does it give you? It says del dot E, so it is minus delta over delta t del dot A here, that is the first part, minus del dot del phi, but that is equal to minus del squared phi. That is called the Laplacian of this phi, right? And it has got its own interesting set of properties which we will come to a little later, and that is equal to rho over epsilon naught. So let us put the minus sign here and put epsilon naught here, and use this. plus and there is a plus, and that is the first equation. We took care of these two equations, we need to take care of this equation here, and it says the curl of E, the curl of E is of course minus delta, pardon me, the curl of B. So it says del cross A, this guy here, minus mu naught epsilon naught. By the way, let us anticipate things a little bit. Mu naught epsilon naught has the dimensions of 1 over the square of a velocity, and it is conventionally called c squared, the speed of light in vacuum. So let me just put that in. So this is equal to minus 1 over c squared, the time derivative, but you got to differentiate a second time, that becomes a plus over dt2 plus 1 over c squared delta E over delta t, that is gradient of delta phi over delta t equal to mu naught j. This fashion. And now we have this famous vector identity for the curl of a vector field, and what is that identity? Gradient of the divergence of A minus del squared A, right. So the curl A or del cross A equal to the gradient of the divergence of A minus del squared A. Del squared is a scalar operator and it acts on each component of A, so it produces a vector field which in Cartesian coordinates has components del squared A1, del squared A2 and del squared A3. That is what that del squared stands for. In case you have forgotten this identity, it is not hard to derive because we want the curl here, so put an epsilon ijk and then del j of del cross A, the k component, that is equal to epsilon k Lm del L Am, and then you move this thing back here and write this as epsilon ijk epsilon L Mk del j del L Am, and that by the identity is delta IL delta Jm minus delta Im delta JL del j del L Am, and now use the Kronecker delta to simplify this matter, and then you get this identity here. So it is a very simple thing, you do not have to remember anything, you just have to remember the fact that when you contract this epsilon symbol once, the answer is in terms of delta functions. Okay. So let us put that back in here, and you got del of del dot A, and there is another del which is sitting here, so let us call it 1 over c squared delta phi over delta t, and I took care of this term and the first term here, plus 1 over c squared d2a over dt2 minus del squared A equal to mu naught j. These are the two equations, I erase this and I have to deal with these two equations. Now that exhausts all four Maxwell equations. The price you paid is that the equations order has increased to second order differential equations. Yes. A Laplacian of a scalar function simply says, so if you got phi, it is d2 phi over dx2 plus d2 phi over dy2 plus d2 phi over dz2. This is what del squared on a scalar function is, but then del squared of A, a vector A, would be A1 unit vector in the x direction plus A2 unit vector in the y direction plus A3 unit vector in the z direction, and these are constant vectors in Euclidean space, so they do not get differentiated, and therefore it stands for a vector with components Ex times del squared A1 and then Ey times del squared A2 and so on. So it is just a shorthand notation for 3 del squareds acting on A1, A2, A3, and it is a vector created out of these 3. Okay. Yeah.
When we define del square phi, we do it in terms of the Cartesian coordinates.
You do not have to do that, yeah.
So for the other two, we are able to define it as the ratio of the integrals.
Pardon me?
For the divergence and for the
Yeah.
gradient.
Yeah, yeah.
We can use the theorems to actually define the.
Right.
But this one, is it possible to
Ah,
define
okay, good question, very good, deep question like everything else. His point is the divergence is really not defined as del dot A, the divergence of A. For a vector field A, the divergence is defined as the flux per unit volume at each point in a limiting case, and an algorithm for calculating that quantity turns out to be del dot A. Similarly, the curl is not defined in terms of these ridiculous determinants or anything like that, it is not del cross A, but rather the circulation of this vector field over a small line integral at each point divided by the area. So it is the circulation per unit area in the limit in which the area goes to 0. An algorithm for calculating it is del cross A. So his question is there a similar thing for del squared? What is the significance of del squared and so on? I will not answer that question directly, it is a scalar operator del dot L del, but I would like to mention though that the reason the del squared operator appears is very profound and very deep, very deep. It is really buried in differential geometry. The del squared operator, or rather the generalization of the del squared operator to complicated spaces, is a very basic property. It probes very basic properties of the space itself. So I know it is an unsatisfactory answer at the moment, but let me not leave it at that. Let me give you a physical picture of why the del squared operator has the kind of role that it plays, and let us go back to electrostatics, look at it and see what it does and what the del squared does. It's a good digression, good to understand that. Oh, incidentally, just a minute, if you did not have time dependent fields but you had only electrostatics, then of course you know this goes away and you got del squared phi is minus rho over epsilon naught. Imagine for a minute rho is time independent, J is time independent. What do you call that equation? Poisson's equation. That is the fundamental equation of electrostatics. And what is the primary property of charge free region where del squared phi is 0? There are no absolute maxima or minima. This is the primary property, and you have the mean value theorem, and it says the value of the field at any point where del squared phi is 0, the value of this phi at any point is the arithmetic mean of all points, the values at all points symmetrically situated about it.
That potential is different from this potential.
Whenever you have Laplace's equation, that is true, that is the statement I am making. Of course you put a source, it is no longer true, but what I am trying to bring out here is the significance of the Laplacian operator. Now when you say del squared phi equal to 0, it says phi is a function, an eigenfunction of the del squared operator with 0 eigenvalue. It is called a harmonic function, and the question is what is so harmonic about it, and the answer I am giving is that this function is such that every solution of Laplace's equation is such that the value of the function at any point is the arithmetic average of the values at points symmetrically situated about it in whatever be the number of dimensions. Well, let me go one step further back. Let us look at Laplace's equation in one dimension. That is my Laplace equation in one dimension, just the second derivative is 0. Now what is the solution to this equation? A linear equation, linear function, right. So it tells you that phi equal to ax plus b. So let us plot this phi as a function of x, this is what it is. What is so special about a straight line? I want the value at every point, the slope is constant. What does it lack? Well, the first derivative is non-zero, it has no maxima or minima, that is certainly true, but even functions which are not straight lines will have no. What does it lack? Its first derivative is non-zero in general, but the second derivative is identically 0. What does the second derivative measure? The curvature. It has no curvature. This function has no curvature. So the consequence of that is that if you took the value at any point here, it is guaranteed to be the arithmetic mean of values symmetrically situated about it, of this value and this value. So if this is x and this is x minus epsilon, x plus epsilon, you are absolutely guaranteed that f of x equal to f of x plus epsilon plus f of x minus epsilon divided by 2. You are guaranteed that. On the other hand, if the function had curvature, then if it had curvature like this, the value here is smaller, the value at this point is larger than the arithmetic mean, and if it were curved the other way, the value out here is larger than is smaller than the value than the arithmetic mean. Only if the curvature is identically 0 do you get this mean value property, and of course it does not take long to realize that I could write this as f of x plus epsilon minus twice f of x, which I will write as f of x minus f of x minus f of x minus epsilon, and that is equal to 0. For good luck I divide this by epsilon, and this is of course the derivative from the right, and this is the derivative from the left, and I divide by one more epsilon and take the limit, and what derivative do I get? The second derivative, and that is exactly this. So you see a harmonic function, this is a harmonic function in one dimension, only a straight line, but you are guaranteed that the value at any point is the arithmetic average of points on either side of it. Now in 2 or 3 dimensions, in 2 dimensions for example, this same property would translate to something much more interesting, because if you have d2 phi over dx2 plus d2 phi over dy2 equal to 0, then of course if you put phi equal to ax plus b plus cy plus d, this is true, that is a trivial case, but you have more interesting possibilities. It is possible that the x derivative d2 phi over dx2 is some quantity and the y derivative is minus that quantity. So the functions do not have to be linear, but they could still satisfy this property, and it is not very hard to see if I did the same trick as what I did there, that the value at any point is the arithmetic mean of the value here, here, here and here. I take these 4 points, x minus epsilon, x plus epsilon, y minus epsilon, y plus epsilon, and I divide by 4 after summing them, and I would end up with that equation in the limit, the second. But then the del squared operator is spherically invariant, it is a scalar operator. So I could in fact have taken 4 points, this, this, this and this, and I would still have this. I could take all these 8 points and do 1/8 and I would still have it, and in fact I could go the whole hog and take all points on this circle and divide by the length of the circle, and I would have a value in the middle. That is the harmonic property, and in 3 dimensions it is a sphere. As you know, this is the property of harmonic functions, the mean value property, any number of dimensions. So that is what is so basic about the del squared operator. Its eigenfunctions give you the generalization of a function without curvature in one dimension, which satisfies this mean value property. So that is why it is so special, this thing. It has other reasons why this is very particular. In fact, if you know the spectrum of the Laplacian operator in a domain, you actually know everything about the domain in some sense. So that is the reason it is a very basic probe intrinsically. By the way, in electrostatics this has the consequence that a function which satisfies this cannot have a maximum here, because it can't be larger than all these values and still be its average, their average. It can't have an absolute minimum here, and the consequence of that is that in a charge free region you cannot put a charge held together by electrostatic forces alone and expect it to be in stable equilibrium. Could be equilibrium but unstable. Some of these terms would be positive, some would be negative. If it is an absolute minimum, all of them would have to be positive and they can't add up to 0. If it is an absolute maximum, all of them would be negative, they can't add up to 0. So you would always have saddle points, some positive, some negative, and you would have unstable equilibrium. And what is that theorem called? Earnshaw's theorem. It just says the del squared function which satisfies Laplace's equation can't have an absolute maximum or minimum at a point. Okay. So let us come back to where we were. Now we have to deal with these 2 equations, and the bad news is that this equation, which looks almost like Poisson's equation, has this A sitting here. What does this equation look like if you did not have this term? It looks like the wave equation, it looks exactly like the wave equation. So there is a 1 over c squared, the second derivative with respect to time, minus the del squared is a 3-dimensional wave equation with a source term on the right hand side. And there are mathematical methods for solving the wave equation, just like there are for solving the Laplace's equation or Poisson's equation. Unfortunately you can't use them directly because the A equation involves phi and the phi equation involves A. It would be glorious if you can put this equal to 0, or if you can put this equal to 0, and now I put it to you that you can always put it equal to 0. A is arbitrary. Is A arbitrary? Well, remember that the physical fields are E and B, they are my physical observables, they carry energy, momentum and so on, I can measure them. So these quantities are specified by the sources and suitable boundary and initial conditions, but these quantities are auxiliary quantities, and the question is, are they uniquely specified or not? It is quite clear if I add a constant vector to A, the fields are not going to change because the derivatives do not act on constants. Similarly, if I add a constant scalar to phi, nothing is going to change, the gradient is not going to change, but there is more to it than that. You can add a lot more to it than that, and let us look at that. And this is going to be exploited, and I am going to finally tie it down to the non-uniqueness of the Lagrangians. So let us do this carefully, and this is called gauge. Gauge invariance. Okay. Now the question we are going to ask is, okay, I say B is the curl of A, and B is a physical field, presumably unique in every given situation. Is A unique or not? This is the question you have to answer. Is this unique? For a given B, is A unique or not? This is the question we have to answer. Apart from a constant, I can always add trivial constants, but is it unique? I can actually, the fact is the curl of any gradient is identically 0, therefore to A I can add the gradient of any arbitrary scalar field and B would not change. So it is quite clear that A as well as A prime, which is A plus the gradient of any scalar field of space as well as time, does not matter, would lead to the same B, because the curl of this gradient would be identically 0. So A is not unique. In classical physics at least, A is not directly physically measurable, it is not unique at all. B very much is, but then we have to be careful. If I change A to A prime, I may also change E unless I compensate for it with phi. So what I should say is that simultaneously with changing A to A prime by adding the gradient of a scalar, I should also change phi to phi prime, which is phi minus delta chi over delta t, minus because there is a minus sign here, I need to compensate for it. And it is now trivial to check that B and E would be the same if you had the scalar and vector potential specified by the pair phi and A, or the pair phi prime and A prime, makes no difference. This is called gauge invariance, and the word is historical. It was pointed out in the early part of the 20th century. It comes from something called Eich invariance, which Hermann Weyl introduced, and it got translated into English as gauge, like the meter gauge or the broad gauge and so on. It was actually a word for measure of some kind, so we will not worry about the historical antecedents of this word, but it stuck. It is called gauge invariance. At this level it looks like a trivial mathematical ploy, but this principle of gauge invariance, when you translate it to quantum mechanics and then quantum field theory, turns out to be perhaps the most basic dynamical principle of all, because all the fundamental forces of nature are taken to be mediated by quantum fields which are called gauge fields, and it arises from a generalization of this idea in electromagnetism. So it is not a trivial mathematical artifact, it is very much rooted in reality. We will see even at this level what it implies. So I put it to you once again that A phi and, well, let me write it the other way because there is a reason for it. Phi prime A prime imply the same E and B. Yeah.
Why should we take a phi prime? Because when we derived the second equation,
Yes.
we actually substituted B equal to curl of A and derived it. So even if we had used an A prime, it
Yes.
shouldn't have mattered.
Oh, it does, because you can see E is going to change. If I change A to A prime, I have added an extra term which is minus delta over delta t gradient of chi, but B must be unique, and the only way I can get rid of it is to simultaneously change phi.
No, but when we derived E,
Yeah.
we actually substituted B equal to curl of A. Instead, we could have substituted curl of A prime and derived that.
Then you would have discovered that E is equal to minus delta A by delta t minus grad phi plus delta chi over delta t. Quite right. If you had used A prime there, you would have added this delta chi prime over delta t. It would have turned out that way. Definitely, yeah. Which two equations? These two? We haven't even come to it yet. We haven't even come to that yet.
But then should we show that the A prime and phi prime also are solutions for those equations that are consistent with all 4 equations?
These equations would of course change, but these are not the equations for E and B. Her point is, should these equations also remain unchanged? And my answer is no, they won't remain unchanged, they will very much change, and that is the whole point. I want them to change because they are equations for A and phi, but the physical fields are E and B, and I simply have to make sure that no matter what pair A and phi I choose, subject to this freedom, the same E and B are produced at the end. No need, no need at all. No need why A prime and phi prime should satisfy it at all. A and phi satisfy this equation. I do not know what A prime and phi prime satisfy at the moment, and I do not care, and that is the whole point. I am going to ensure that I choose my chi in such a way that A prime and phi prime satisfy a simpler set of equations. But since I am guaranteed that A prime and phi prime do the same job as A and phi as far as E and B are concerned, I would like to solve an easier problem. It is a little bit, just to give you an analogy, it is a little bit like saying I give you a set of a vector equation, I could solve this in Cartesian coordinates or spherical polar coordinates. There may be some symmetry in the problem which causes the problem to be simpler in spherical polar coordinates. I use that, and after I do it, I translate the solution back to Cartesian coordinates. I do not lose anything, right. So this is exactly what is going to be done. I am going to exploit this freedom. Rho and J are physical quantities, absolutely. A and phi are auxiliary quantities. No, please let us understand. These two are specified. You are not solving these equations in order to find rho and J. You are solving these equations in order to find A and phi, and therefore E and B. So rho and J are given to you, they are not changed, they are gauge invariant, no question. E and B are gauge invariant, but A and phi are not. They are intermediate quantities, they are auxiliary quantities, and my claim now is that this freedom is what I am going to exploit in order to simplify that set of equations. So now here is what I do. I say, okay, you have given me this freedom, and I come back to this equation and I am going to do exactly what she suggested. Put this in there and see what happens. Now I put it to you that I can choose my chi in such a way, so let me not clutter up the notation, but I will say it in words, it is easy enough to understand. I will choose my chi in such a way that this equation becomes del squared phi prime equal to minus rho over epsilon naught without this term. How do I do that? Well, I first pretend that I have been stupid enough to choose some A and phi, and that is my equations to start with, and let us suppose del dot A is not 0. I have chosen an A and I calculate del dot A and I find it is not equal to 0. What can it be? Well, it is equal to this. Del dot A is a scalar quantity, so it is equal to some f of r and t. it is some f of r and t. Then what is del dot A prime? It is equal to del dot A, which is f of r and t, plus del dot del chi, which is equal to del squared chi of r and t. And I set this equal to 0. I set it equal to 0. How would I do it? By choosing chi to be a solution of del squared chi equal to minus f. So no matter what A you give me, I find out what its divergence is and I find it some function f of r and t, then I immediately switch to an A prime, which is A plus the gradient of chi, where I choose chi, and that is up to me to choose this chi, such that it solves the equation del squared chi equal to minus f. That is Poisson's equation and I know how to solve it. So choose chi is called the gauge function, such that it is a solution of del squared chi equal to minus f. Very good question. Can that equation be solved? Now I have to put conditions under which Poisson's equation can be solved. This is a well posed problem in the theory of partial differential equations. If you specify appropriate boundary conditions, Poisson's equation can be solved. It is guaranteed that a solution exists. I will not go into the technicalities of when it exists and what conditions and so on. In all the normal electromagnetic problems, this would be solved. In fact, we are going to write the solution down. Pardon me? Which second term? This I have not done anything, I have not gone here at all, I am just saying you give me a del dot A, you give me an A, I calculate del dot A, I discover it is some function not 0, I promptly choose an A prime related to A through this such that del dot A prime is identically 0. That means you give me f and I tell you what chi is.
In a closed analytical form?
Not necessary. Yes, in a closed analytical form. Yes.
But I don't understand when that equation is not solvable.
Let me give you an instance. If this you have to now specify things like, is it differentiable, is this f very bad, I have to after all integrate this equation, so is that f integrable. So I have to answer technical mathematical questions of this kind, but we are going to use physical arguments to write down a solution to Poisson's equation. I will do that from Coulomb's law, which you already know. So we write down a free solution to the Poisson equation, but take it from me at the moment as an assertion that you can solve Poisson's equation. There are tables, there are mathematical algorithms to solve Poisson's equation. Therefore in principle, no matter what A you give me, I can rewrite this equation in terms of A prime and phi prime, where del dot A prime is 0.
If I can make the del dot A equal to constant, then also the term will go to 0.
Yes, I can make del dot A equal to some constant, yes, instead of 0, and then this is again 0 here, and therefore this is certainly true. Yes, I can do this, but if I can make it a constant, why do you want this constant? Why don't I make it 0? I can do it just as easily to do that, right? But if you are right, there is nothing unique about the choice of this gauge. Yes, we are trying to find E and B. We have written these equations in terms of A and phi, but A and phi are not unique because it is some derivatives of them which give you E and B, and you can put various arbitrary gradients and so on to be added to A such that E and B do not change. But the auxiliary equation for A and phi, I would like to use this freedom to write in as simple a form as possible. In particular, it would be very nice if I could decouple the phi equation from the A equation, and that is what is achieved if I put this equal to 0. Then there is no A dependence here, it is only phi. I should call it phi prime, but so I am going to take this as a given and say that I can always choose my gauge such that del dot A is 0, in which case the first equation becomes Poisson's equation again for phi or phi prime, but I will drop the prime. I will assume that you have chosen del dot A equal to 0. This is called the Coulomb gauge. Yeah.
So we have written the equation for A prime and phi prime
Right.
independent
Yes, yes.
And then you just now said that a prime and phi prime did not satisfy these equations.
No, let me put that in. So I choose this, a prime, and instead of a I now write a prime minus grad chi, and instead of phi I write phi prime plus delta chi over delta t. I put that in here, and then the statement is del dot a prime is 0. Okay. So where does that leave you? It leaves you with Poisson's equation for the scalar potential. So the sum and substance of this entire thing is you can use gauge invariance, the freedom in the choice of the vector potential, to ensure that the first of these equations, this equation, reduces to Poisson's equation for the scalar potential, because the statement is you can always choose your gauge such that del dot A is 0. If you want to call it A prime, that is okay.
So we have simplified this equation, but that might complicate the another equation.
Good point. Once you simplify the first equation, you may be in deep trouble in the second equation, but let me say what happens. That is a good point. You have to worry about that, but then what I am going to say is, if you permit me to get rid of this, and this is called the Coulomb gauge. So if I work in the Coulomb gauge, then the first equation becomes Poisson's equation, and I claim I can solve Poisson's equation. I am going to show you how. We will write down a solution. Then phi becomes known to you, this is known to you, and then you put it in here, this is known to you, and this is 0. So move this known to the right hand side, and then it says A satisfies a wave equation with a known right hand side, and if I can solve the wave equation, then the problem is done in principle, at least in principle it is done. And after that, if you find A and phi, then you differentiate and you find B and E. So all of electromagnetism is solved in the Coulomb gauge. But the important point is, and I want to assert this again and again, that you can always work in the Coulomb gauge. This is always possible. Whether it is advantageous to do this or not is a different question, whether you want to do it or not is a different question, but it decouples the two equations, the A and phi dependencies, and it reduces the problem to solving the Poisson equation for phi and the wave equation for A, and these are well studied mathematically, well posed problems that solves all of Maxwell's equations. But you can take another tack, you can say I do not like that, can I not use the gauge freedom to put this equal to 0? If I did that, I would just have the wave equation for A. Can I always do that? The question is, can I always do this? And the answer is, what is it that you have here? You got del dot, if I put A prime here, then I got a del squared chi minus 1 over c squared d2 chi over dt2 equal to whatever this quantity is. So I give the same argument and I say, suppose you find that del dot A plus 1 over c squared delta phi over delta t equal to some g of r and t, say suppose it is equal to some g, not 0 but some g. Then I go to phi prime and A prime and I choose my chi such that 1 over c squared d2 chi over dt2 minus del squared chi minus g. Just as I chose my chi here to be a solution of Poisson's equation, I choose my chi there to be a solution of the wave equation, and the assertion is I can solve the wave equation subject to conditions and so on, and once I do that I am guaranteed that del dot A prime plus 1 over c squared delta phi prime over delta t is 0 identically. So in that gauge this quantity can be set equal to 0, or rather with A prime phi prime. My assertion is you can always set this to 0, always. Can you do both? Can you set this to 0 and that to 0? No. The reason is Gauge freedom gives you the freedom to handle to choose only one scalar quantity chi. So if you choose that chi to be a solution of the wave equation, there is no reason why it should also satisfy the Poisson equation, and vice versa. So you have only one piece of freedom to do. Can I choose therefore a gauge in which A is always 0, the vector A? No, physically you know if there is a magnetic field A need not be 0, it will not be 0 in general. So you can't do that because A is a vector and chi is a scalar function. Incidentally, a gauge in which this is 0 is called the Lorentz gauge. There are cases where this is more advantageous than this gauge. Can you tell me why? Why you would think that this is setting this to 0 is better than setting that to 0? You can always do it in any given problem, you can do either this or that. Why would one be preferable to the other? Well, okay, again the same question. Suppose I solve this equation in the Lorentz gauge, then I find A, I put that in here, so this becomes a known, I take it to that side and solve Poisson's equation. So once again, but why is it conceivable? But why is it conceivable that the Lorentz gauge is any better than the Coulomb gauge? But why is it conceivable that the Lorentz gauge is any better than the Coulomb gauge? Then I have no problem, I just said phi equal to 0 and I am done. If I have electrostatics, can I do this? I do not have magnetic field, I have a constant uniform electric field in the x direction independent of space and time. Everywhere in space I have a constant field. Can I choose phi equal to 0? You really think so? You have to have faith in this because I just put it to you that there is one piece of information chi and there is a scalar function, you can choose that in many ways, and the claim is yes, you can always make phi equal to 0. You can always choose a gauge such that phi is identically 0. May not be a very good thing to do, but let us look at this example we talked about. I have E of r and t to be equal to E naught Ex, that is it, where E naught is a constant, no space dependence, no time dependence, and B equal to 0. And my question is, can we choose a gauge in which phi is 0? Yes, I can. I can choose phi of r and t to be identically 0, and I choose A of r and t to be equal to minus E naught Ex t. Choose that. So I have a vector potential, no scalar potential, no magnetic field, and of course del cross A is 0 because this is a constant vector and this involves only time, so there is no magnetic field, but then minus delta A over delta t, that gives you this field. So you can do electrostatics using only a vector potential and no scalar potential. Even in the simplest of electrostatic problems you can use a scalar potential to be identically 0. It would of course be very stupid to do this, and the reason it would be stupid is because the whole purpose of the game is to find the fields, and now I am giving you a vector potential which is constructed to give you this field, so I have to tell you the field before I tell you what the field is, and then I go through the potential, so there is not much sense in doing it, but the point is in principle this is okay. So please remember that all electric fields are not minus the gradient of a scalar field because these are not all irrotational. The moment you have a magnetic field which is changing with time, you immediately have an electric field whose curl is not identically 0, therefore which cannot be written as the gradient of a scalar. And even in cases where you have electrostatic fields of this kind, you could work completely with a vector potential and no scalar potential at all. Do this. Similarly, you can choose a gauge in which delta phi over delta t is 0. You can choose a gauge in which phi is 0. You can choose a gauge in which del dot A is 0. you cannot choose a gauge in which A is 0 because that is a vector. You can't choose a gauge in which, it is not common, you can't choose a gauge in which the magnitude of A is a given constant, because this would involve technicalities, because the magnitude would involve square root of ax squared plus ay squared plus az squared, and once you bring in square roots and singularities and so on, the problem becomes different altogether. We have been talking about non-singular gauges of this kind. There are singular gauges, but the simplest possibilities are, as I said, most standard possibilities are either the Coulomb gauge when this is 0 or the Lorentz gauge when this is 0. And now what I am going to do is to write down next time the solution to Poisson's equation. We will work backwards from Coulomb's law, which you already know, plus the superposition principle, and then I show you how to write the solution down for the wave equation. Now once we do this, then we have to address the real problem, and that problem is what happens if you have a charged particle moving in an electromagnetic field. What is the Lagrangian, what is the equation of motion, and our target is to find the Lorentz force equation. This is the equation of motion, and the question is how are you going to derive it. So I give physical arguments to write down the Lagrangian and then use that, the Euler-Lagrange equations, to derive the Lorentz force. So this will be the next task. And finally I will comment on why the particular choice of Lagrangian, it is again buried in relativity. All of electromagnetism is buried in that. And finally the last point I want to make is that these are first order differential equations, unlike Newton's equations of motion. The original Maxwell equations are first order differential equations, and the structure of these equations is such that there is Lorentz invariance built in. It is the same for all frames of inertial frames of reference, that requires this set of equations to have the structure that they have at the moment. You can see this in another way, in a very heuristic and crude way. Once you have relativity, spatial and temporal coordinates get mixed up. So if you have first order derivatives in space, you cannot have second order derivatives in time, they must also be first order. So that is the reason why the time evolution equations are also first order partial derivatives in this thing, but this is fine. I mean, as long as the problem is mathematically well posed, we can handle this. So I hope I have given you a sort of in a nutshell a summary of what the basic problem is in classical electromagnetism. Now we are going to couple it to the matter fields, to charged particles, and see what happens then. I will do that next time. Okay.